Myself, Dr. P. Soumya, working as an assistant professor in the Department of Chemistry at the Institute of Aeronautical Engineering College. In this session, I'm going to discuss about electrode potential and reference electrodes. So, in this session, I'm going to discuss about electrode potential, standard electrode potential, reference electrodes, and the reference electrode, standard hydrogen electrode, and Calman electrode. First, we should know what is electrode potential. What is electrode potential? So, when a metal is placed in a solution of its own ions, when a metal is placed in a solution of its own ions, the metal acquires either positive or negative charge. The metal acquires either positive or negative charge with respect to the solution. On the account of this, the definite potential difference is developed between metal and the solution, means metal and electrolyte solution. So that potential is called as electrode potential. So when we place a metal in a electrolytic solution, so that metal acquires either a positive or negative charge because of the solution which is present in that electrode. So we will get negative or positive charge. So the potential difference is developed between the electrode and electrolyte. If metal acquires positive charge, the negative ions will surrounded around the metal. Negative ions surrounded around the metal. If metal acquires negative charge, positive ions surrounded by the metal. So, because of the charge difference, positive, negative, positive, so there is a developed potential difference between the metal and electrolyte solution. So that is called as electrode potential. So if the metal undergoes oxidation, then the positive metal ions may pass into the solution. So means here oxidation occurs. So metal ions converted to electrodes converted to metal ions by the liberation of electrons. So that reaction is called as oxidation. If the metal undergoes reduction, then the positive metal ions from the solution may get deposited over the metal. So means metal ion will accept some electrons and it will form metal. So this is about electrode potential. So this electrode potential is the magnitude of electrode potential depends on the concentration of ions, temperature and nature of electrode. The magnitude of potential depends on concentration of ions, temperature and nature of the electrode. Concentration of ions means concentration of electrolyte. This is next one is it will dependent on temperature of that experiment. So it will depends on the nature of the electrode. So in order to compare the electrode potentials of various electrodes, it is necessary to specify concentration of the ions present in the solution and the electrode which is dipped and the temperature of the half cell. So in order to compare the electrode potentials of various electrodes, it is necessary to specify the concentration of ions as well as temperature of the half cell. So next topic is single electrode potential. So in the electrochemical cell, we are having two electrodes. So one is acts as anode and second one is acts as cathode. One will act as cathode, one will act as anode. this will act as anode and this will act as cathode. So at anode, oxidation takes place, means the electrons are evolved. Electrons are evolved. At cathode, reduction takes place, means electrons are consumed. Electrons are consumed. So each electrode dipped in its salt solution is called as half cell. Means this is one half cell, this is second half cell. This is anodic half cell, this is cathodic half cell. So the potential of one half cell is called as single electrode potential. The potential of single half cell is called as single electrode potential. Next one is standard electrode potential. Next topic is standard electrode potential. The potential difference developed between the metal electrode and the electrolyte of its own ions of unit concentration at 25 degrees centigrade and at 1 atmospheric pressure is called as standard electrode potential. So what mean by standard electrode potential? So potential difference between the electrode and electrolyte of unit concentration at 25 degrees centigrade at 1 atmospheric pressure. If we measure the electrode potential at standard conditions, so that potential is called as standard electrode potential. What are the standard conditions? Standard conditions are the concentration of electrolyte. Concentration of electrolyte should be 1 molar. Concentration of electrolyte should be 1 molar and temperature should be maintained 25 degrees centigrade. That is in Kelvin 298 Kelvin. So pressure is 1 atmosphere. 1 atmosphere. So by maintaining the standard condition, if we measure the potential of some electrode, so that potential is called as standard electrode potential. The potential difference developed between metal electrode and electrolyte of its own ions of unit concentration at 25 degrees centigrade and at 1 atmospheric pressure is called as standard electrode potential. Standard electrode potential. So it is denoted by E naught. It is denoted by E naught. So next, standard reduction potential and standard oxidation potential. So what is meant by standard reduction potential? So the standard reduction potential is the tendency of chemical species to be reduced. That is called as standard reduction potential. So the standard reduction potential is the tendency of a chemical species to be reduced. That is measured in volts at standard conditions. So what is standard oxidation potential? The standard oxidation potentials measures the tendency of a given chemical species to be oxidized at standard conditions. So what is a simple definition of standard reduction and oxidation potentials are, when we measure the potential difference between metal and metal electrode during the reduction process at standard conditions, so that will give standard reduction potential. So what is standard oxidation potential? If we measure the potential difference between metal and electrolyte during the oxidation process. During the oxidation process means loss of electrons. Metal will convert to metal ion and electrons. Here metal ion accepts electrons and form metal. So during the reduction process, if we measure the reduction potential, that is called, we measure the potential of the electrode and electrolyte, that we will call as standard reduction potential. If we measure the potential difference between electrode and electrolyte during the oxidation process, that potential is called as standard oxidation potential. So next topic is electromotive force. Electromotive force. So this is also potential difference between the electrodes. The EMF is the potential difference between electrodes, which is the driving force for the flow of electrons, is known as electromotive force. The potential difference between two electrodes. Here, electromotive force means the potential difference between two electrodes, which is the driving force for the flow of electrons. So that is called as electromotive force. So EMF of a cell potential is measured in units volts and also referred as a cell voltage, means it will denoted as E cell. It will denoted as cell voltage. So of EMF equal to oxidation potential of anode and reduction potential of cathode. Oxidation potential of anode plus reduction potential of cathode. So we know that we have in one electrochemical cell, we have two electrodes which are dipped in electrolytic solutions of its own ions. So if we take this is as a zinc, so it will dip in the zinc sulfate solution. If we take copper electrode, so it will dip in the copper sulfate solution. So these are separated by one salt bridge. So these two are connected with the voltmeter. So this is called as electrochemical cell, galvanic cell. So if we take these two electrodes at one half cell, oxidation is taking place. Oxidation is taking place. At second one, reduction is taking place. Reduction is taking place. So if we measure the EMF of the cell, so what is mean by here? Oxidation occurring, here reduction is occurring. If you measure the potential at during the process of oxidation, that potential is called as standard reduction oxidation potential. Standard oxidation potential. If you measure the potential of an electrode during the reduction process, that is called as standard reduction potential. So EMF of the cell equal to oxidation potential of anode and reduction potential of cathode. Oxidation potential of anode plus reduction potential of cathode. So reduction potential of electrode and oxidation potential of electrode in magnitude both are same, but only the sign but these are having opposite sign. These are having sign. So the reduction potential of electrode is equal in magnitude but opposite in sign. So to its oxidation potential means, so reduction potential equal to minus oxidation potential. Oxidation potential as well as oxidation potential equal to minus reduction potential. So for example, I am taking, if zinc is having some 0.76 volts, so this reduction potential, I am taking reduction potential of zinc oxidation potential of zinc in zinc plus 2. So that is 0.776 volts. So this is oxidation potential. We can write the reduction potential is minus 0.76 volt. Means reduction potential equal to minus oxidation potential. So only sign will change, not magnitude. So EMF equal to reduction potential of cathode and reduction potential of anode. Here first equation, EMF equal to oxidation potential of anode, reduction potential of cathode. So we know that oxidation potential of anode is minus reduction potential of anode. So reduction potential of cathode minus reduction potential of anode. So this is the representation of EMF. So E cell equal to E cathode minus E anode. So this is nothing but E cathode minus E anode. So E right minus E left. Next representation is E cell equal to E right minus E left. So if we want to write in oxidation potential, so EMF is equal to oxidation potential of anode minus oxidation potential of cathode. Oxidation potential of anode, oxidation potential of cathode. This is about EMF. So applications of EMF. Applications of EMF measurement. So this can be used for the potentiometric titrations, and transport number of ions can be determined by using EMF. pH can be determined, and also hydrolysis constant, and also solubility of sparingly soluble salts can be found by using EMF measurement. So what is reference electrode? So reference electrode is the electrode with reference to those the electrode potential of any electrode can be measured. So with reference to those, the electrode potential of any electrode can be measured is called as reference electrode. Means we are taking as a reference. So it can act as anode or cathode depending upon the nature of other electrode. Depending upon the nature of other electrode. So another definition is reference electrode is an electrode whose potential is arbitrarily taken as 0 or whose potential exactly known. Whose potential is exactly known. Whose potential is arbitrarily taken as 0 or whose potential is exactly known is called as reference electrode. So reference electrodes are two types. Reference electrodes are two types. One is primary reference electrode, second one is secondary reference electrode. Primary reference electrode and secondary reference electrode. What is primary reference electrode? The reference electrode whose potential is taken as 0. Whose potential is taken as 0 is known as primary reference electrode. Is known as primary reference electrode. Example of primary reference electrode is standard hydrogen electrode. This is denoted by SHE. So standard hydrogen electrode. So what is secondary reference electrode? The reference electrode whose potential is not 0 but exactly known. Whose potential is not 0 but exactly known, that electrode is reference electrode is known as secondary reference electrode. The electrode potential value depends on the concentration of the solution in which it is dipped. Means concentration of electrolyte. Concentration of electrolyte. So examples of secondary reference electrodes are saturated calomel electrode and silver chloride electrodes. Saturated calomel electrode and silver chloride electrode. The saturated calomel electrode denoted as SCE. Standard example of primary reference electrode is, first one is standard primary reference electrode. Standard hydrogen electrode. So what is the construction of standard hydrogen electrode? So this is the standard hydrogen electrode. It consists of platinum strip. This is platinum strip. So platinum strip is coated with platinum black. Platinum strip is coated with platinum black, which is used for the absorption of hydrogen gas. Absorption of hydrogen gas. So here, so one glass tube is there. So one platinum. This is strip is coated with platinum black, which is used for the absorption of hydrogen gas, and it consists of one platinum wire, which consists of platinum wire, which is connected to the platinum strip, which is connected to the platinum strip, and glass tube. Glass tube. So this is a platinum wire. This is the platinum wire which is connected to the platinum strip, and the hydrogen gas is passed through the inlet, which is having glass tube, one side inlet. So at 1 atmosphere, so next, the electrode is immersed in 1 molar H plus ion. This electrode is immersed in 1 molar H plus ion solution. It may be HCl or H2SO4. Means it is having H plus. So we can take HCl or H2SO4 as an electrolytic solution. So this glass tube, inverted glass tube, is consisting of platinum strip which is connected to the platinum wire at one inlet. From the one inlet, here 1 atmospheric pressure hydrogen gas is passed. So this total glass tube is dipped into the 1 molar H plus solution. So this is the construction of hydrogen electrode. Here the electrode potential is taken as 0 at all temperature. The standard hydrogen electrode potential is taken as 0, arbitrarily taken as 0 at all temperatures. So here we are measuring the potential at 1 atmosphere, and we are taking 1 molar solution and we are measuring it 25 degrees centigrade. So this potential is called as standard electrode potential. So here we are measuring standard conditions. So this is called as standard hydrogen electrode. The cell representation of standard hydrogen electrode is, here we are taking hydrogen which is adsorbed on the platinum. So means this electrode is here in this standard hydrogen electrode. The electrode is hydrogen gas which is adsorbed on the platinum. It can works as an electrode. The electrolytic solution is 1 molar H plus solution. So what is the cell representation? So what is the electrode? Platinum and hydrogen which is immersed in the H plus ion solution. This is the cell representation of standard hydrogen electrode. So if the potential of coupled electrode, if the potential of coupled electrode is greater than 0, then the standard hydrogen electrode acts as anode. For the measurement of unknown electrode potential, so we have to couple the standard hydrogen electrode with the other electrode. So if that coupled electrode is having higher potential, so then the standard hydrogen electrode acts as anode. So then at anode, what will happen? Oxidation is taking place. So hydrogen undergo oxidation and forms 2H plus 2 electrons. So hydrogen gas undergo oxidation and forms 2H plus and 2 electrons. If the coupled electrode is having electrode potential greater than 0, then standard hydrogen electrode acts as anode and oxidation reaction is taking place at the electrode. If the potential of coupled electrode is less than 0, then the standard hydrogen electrode acts as cathode. The electrode reaction can be written as, so here what will happen? Reduction takes place. Means the electrolytic solution we are having H plus ions, this will undergo reduction by accepting electrons and form hydrogen gas. gas. If the potential of coupled electrode is less than 0, the standard hydrogen electrode acts as cathode and reduction takes place. So means two H plus ions which are present in electrolyte solution, they will undergo reduction and forms hydrogen gas. So, limitation of standard hydrogen electrode. Limitations of standard hydrogen electrode. Standard hydrogen electrode is difficult to construct. It is difficult to construct because bubbling of hydrogen gas at 1 atmosphere around the platinum through the solution is difficult. Bubbling of hydrogen gas at 1 atmosphere around the platinum through the solution is difficult. So, construction of SHG is difficult and maintaining activity H plus at unity is difficult. Maintaining the activity of H plus at unity is difficult. Means here we are taking 1 molar H plus ionic solution. H plus ion solution. So, maintaining 1 molarity of the H plus ions is very difficult. So, platinum has high absorption and catalytic activity. So, hydrogen on platinum surface can act as reduction catalyst. Reduction catalyst. That's why a number of organic substances are reduced. That's why number of organic substances are reduced. And also inorganic ions like Fe plus 3, MnO4 minus, etc. reduce their lower valence state. And also cations of silver, copper, cadmium, palladium will get reduced and deposit on the platinum metal. Deposit on the platinum metal. And also substances like arsenic and sulfide also interfere. So this is the disadvantages, limitations of standard hydrogen electrode. So measurement of zinc electrode potential using standard hydrogen electrode. So for the measurement of unknown electrode potential, first we have to couple the unknown electrode with the hydrogen electrode, standard hydrogen electrode. Here we are taking zinc electrode. We know already. So zinc electrode which is dipped in the zinc sulfate solution or zinc chloride, any other electrolyte. So we are coupling this with hydrogen, standard hydrogen electrode. So here we are maintaining the 1 atmosphere and at 25 degrees centigrade and 1 molar concentration of standard hydrogen electrode. And also here we are measuring the standard reduction potential of zinc electrode. Standard reduction potential of zinc electrode. Here we are connecting with the standard hydrogen electrode with the salt bridge. Externally we are connected to the voltmeter. Connecting to the voltmeter. So when we connect these two electrodes with each other, we will get one voltage in the voltmeter. So that is nothing but E cell. That is nothing but we will get some voltage. Here we are getting 0.76 volts. 0.76 volts. Already we know that E cell equal to E cathode minus E anode. E cathode minus E anode. So here hydrogen electrode is acts as cathode. Hydrogen electrode acts as cathode. This zinc electrode acts as anode. E cell equal to E cathode minus E anode or E right minus E left. So we know that E cell is 0.76. E cell is 0.76 and the standard hydrogen electrode potential is taken as 0. So we are substituting the 0 here in this equation. So from this equation we will get E anode equal to minus 0.76 volt. Minus 0.76 volt. So this is the electrode potential of zinc electrode. So this is the electrode potential of zinc electrode, that is minus 0.76. Like this, we can measure unknown electrode potentials using standard hydrogen electrodes. So next reference electrode is calomel electrode. This is a secondary reference electrode. Calomel electrode is secondary reference electrode. So calomel electrode is mercury mercurous chloride. Mercury mercurous chloride. Mercury means Hg. So all we know that mercury means mercury. Hg. So calomel electrode is mercury mercurous chloride. It is commonly used as secondary reference electrode. It is commonly used as secondary reference electrode. It consists of thin layer of mercury is placed at the bottom of the container, and it is covered with a paste of mercury mercurous chloride that is called as calomel. The paste of the mixture of Hg and Hg2Cl2 is called as calomel. So that's why this electrode is called as calomel electrode. So in this, this is the standard saturated calomel electrode. So here at the bottom of this glass tube, pure mercury is placed. Pure mercury is placed. So after that, this is covered with Hg and Hg2Cl2. Hg2Cl2. So first at the bottom of the glass tube, if we are placing mercury, and then it is covered with the paste of mercury and mercurous chloride, and this is called as calomel. After this, the remaining part of glass tube is filled with the saturated KCl solution or 1 molar KCl solution. Saturated KCl or 1 molar KCl solution. If we use 1 molar KCl solution, 1 molar KCl solution, that electrode is called as 1 normal calomel electrode. If we use 1 molar KCl or 1 normal KCl, that calomel electrode is called as normal calomel electrode. Normal calomel electrode. If we use saturated KCl solution, KCl solution, so that is called as saturated calomel electrode. Saturated calomel electrode. If we use 1 molar concentration of KCl, that is called as normal calomel electrode. If we use saturated KCl solution, that is called as saturated calomel electrode. So this is about calomel electrode. In this, it is having one glass tube. At the bottom of the glass tube, mercury is placed. This mercury is covered with mercury and mercurous chloride paste. Then remaining part of the glass tube is filled with KCl solution, and which is saturated with Hg2Cl2. And one glass tube is there, platinum wire which sealed into the glass tube. Platinum wire which is sealed into the glass tube, dipped into the mercury layer, which is used for the electrical contact, which is used for the external electrical contact. So this is the construction of calomel electrode. The electrode potential of saturated calomel electrode is 0.2412 volts. Saturated calomel electrode potential is 0.2412 volts. The potential of 1 molar calomel electrode. 1 molar calomel electrode means normal calomel electrode is called as 0.28 volts. 0.28 volts. So this is the cell representation of calomel electrode. Cell representation. Calomel electrode. Here we are taking mercury and mercurous chloride. This is acts as electrode. So which is connected to the platinum wire. So we have to mention 3: platinum, mercury and mercurous chloride, which is placed in the KCl solution of some concentration as saturated or normal. So This is the cell representation of calomel electrode. Platinum HgCl2 in presence of KCl, which is saturated with the Hg2Cl2. This is the cell representation of calomel electrode. So the electrode reaction is, here we are taking reaction. So Hg2Cl2 gives rise to Hg with the and chlorine ions by accepting 2 electrons. This mercurous chloride will accept 2 electrons and forming 2 Hg plus Cl minus. So we know that next equation is equal to E naught minus 0.059 by N log of activity of products by activity of reactants. Concentration of products by concentration of reactants equal to E naught minus 0.059 by N log concentration of products by reactants or concentration of activity of products by activity of reactants. Here what is the reaction? Here we are taking reduction reaction. So Hg2Cl2 accepting 2 electrons and forms 2 Hg plus 2 Cl minus. 2 Hg plus 2 Cl minus. These are the products. These are the products and these are the reactants. So we have to write the concentration here and here. Concentration of products by concentration of reactants. So equal to E naught minus 0.059 N log concentration of products means first we have to write Hg like this and Cl minus 2 by reactants concentration of Hg2Cl2 here where N equal to number of electrons here we are getting 2 electrons here 2 electrons involved in the reactions, so that is nothing but N equal to E naught minus 0.059 by 2 log. So we know that concentration of Hg and Hg2Cl2 or activities of Hg or Hg2Cl2 can be taken as unity, means 1. So 1 into Cl minus, so we can get E naught minus 0.059 by 2 log Cl minus so it can be written as E naught minus 0.059 by 2 log concentration of Cl minus. This will be cancelled out and equal to E naught minus 0.059 into log Cl minus. So this is the cell. So the potential from this equation we can say that. So we are getting is E equal to E naught minus 0.059 log Cl minus and 2. So the potential difference, this is the potential difference. Potential difference of calomel electrode depends on the concentration of KCl solution, concentration of Cl minus. So it is depends on the concentration of Cl minus, nothing but concentration of KCl solution. So from this equation we can say that the potential of calomel electrode depends on the concentration of Cl minus ions which are present in the electrode solution, which is present in the calomel electrode. So we can measure the unknown electrode potential using the saturated calomel electrode as a reference electrode, secondary reference electrode. Secondary reference electrode means it should, the potential electrode potential of saturated calomel electrode is known, exactly known. So this is connected to the saturated calomel electrode is connected to the unknown electrode, and we will get one voltage at voltmeter. So here we are taking example zinc in zinc plus 2 solution. It is connected to the saturated calomel electrode, and internally it is connected to the salt bridge, externally with voltmeter. So when we connect these both electrodes, we will get one voltage in the voltmeter, that is nothing but E cell. So we are getting one voltage, 1 volt. So 1.0 volts. So we know that E cell equal to E cathode minus E anode. Here zinc is acts as anode. In this, the electrode potential of zinc is less than electrode potential of standard calomel electrode. That's why zinc is acts as anode. Standard calomel electrode is acts as cathode. This is acts as cathode. So we know that E cell equal to E cathode minus E right, or E right minus E left. So if we substitute the values, we know that mercury saturated calomel electrode voltage is 0.24 volts. So by substituting this voltage and the E cell voltage, we can get the electrode potential of zinc, which is placed in zinc plus 2 solution. So what is the electrode potential? Here we are getting minus 0.76 volts. Minus 0.76 volts. So from this, we can measure the unknown electrode potential by using standard electrode potential, standard hydrogen electrode, as well as calomel electrode, saturated calomel electrode. So this is about reference electrodes. So merits of advantages or merits of calomel electrodes. Concentration of Cl minus remains constant. Concentration of Cl minus remains constant. Potential of electrode remains constant with the temperature. Potential of the electrode remains constant with the temperature. Ease of oxidation reduction reactions. Here, ease of oxidation reduction reactions. The construction of saturated calomel electrode is very simple and easy to maintain. Very simple and easy to maintain, and is also inexpensive apparatus. pH can be measured by combining. pH can be measured by combining with the hydrogen or glass electrode or quinhydron electrode. pH of the solution can be measured by using this saturated calomel electrode, which is combined with hydrogen or glass or quinhydron electrode. So what are the demerits of saturated calomel electrode? Solubility of KCl is sensitive. Solubility of KCl is sensitive. KCl has to be replaced from time to time. So we have to change the KCl from the time to time in the saturated calomel electrode. Mercury. So here we are using mercury, mercurous chloride. So we know that mercury is toxic and poses health hazard. So these are the demerits and merits of calomel electrode. And thank you.
Like, share and subscribe. Hit the bell icon for more updates.